This is the lesson plan for today. We're going to be discussing or starting our discussions on routing at layer 3. So for this week, we're not going to have any news reviews. We'll continue next week. And we don't have any material left from last week to look at today. Let's take a look at the readings that we have assigned for this and for next week to understand where we are. So let me switch here to Blackboard. So for this week, we have readings 3.3 and 3.4, and notice that it's the same for next week. Additionally, you have sections 9.1, 9.2, and 9.3 from Dordal, which is they're basically the same as the ones from Peterson and Davis. So therefore, I mark them as for support. So I don't need you to look at all the details from Dordal, so just take a quick look at those sections, but focus on the material from Peterson and Davis 3.3 and 4.4 and 3.4, excuse me. And if you go to your Peterson and Davis book, you'll see that 3.3 is routing and 3.4 has to do with implementation and performance at layer number 3. And in routing, it starts with a quick discussion of network as a graph, and then it goes and talks about distance vector, and then how it is implemented in a protocol called RIP, and then it starts talking about link state and a little bit about the protocol that implements, one of the protocols that implements link state, which is OSPF, which stands for Open Shortest Path First. So today what we're going to do is we're going to focus on the actual algorithms for routing. We'll start with a discussion on routing, and then we're going to look at a little bit, talk about distance vector and link state based on the other videos that you watch for this week and your readings. And then we're going to work on a few exercises. Finally, we're going to be talking about how to install GNS3 on your VM on DigitalOcean. So let's start with the material for this week. Let's go and start with routing. Now let's start with a quick discussion on routing and what are the functions that are typically implemented at layer 3. So if you think about the things that we've looked at so far, we know that layer 3 has definitely some addressing. We've also know that it can do store and forward. So routers receive packets, analyze them, and they're going to forward it based on a forwarding table. And now the step for this week and next week is routing. Routers will also be in charge of understanding how to create that forwarding table based on a distributed algorithm called routing. And there's a fourth one, which is common to lots of layers, which is management and control. We'll talk a little bit about this next week in class. So those are the typical functions of a layer 3. The next question that we're going to look at is, well, what is the goal of routing? And the goal of routing is basically to find a path between two nodes or two routers. To find a path, but not any path, to find the least cost path. And we label that as LCP between two routers. And we can extend it just not to two routers, but we can say, well, we want to run that algorithm, the entire network. So we want to look at the network as a whole and find the least cost path between any two set of routers in our network. That's the main goal of routing. When we think about what's the difference between centralized and distributed routing, remember we mentioned that we can do both. And with centralized, we have some disadvantages. And disadvantages is that there's a single point of failure with any centralized system, excuse me. And in particular with centralized routing, we've said that it might not be scalable. So it's not scalable because you'll have a central point that needs to send lots of control information to maybe a very large network. And we also said that these days, this centralized approach is also being considered again in something called software-defined networks. And in distributed routing, It's now it is scalable, but up to a certain point. So we're saying that it's going to be scalable up to hundreds of nodes. If you grow more than that, it becomes infeasible to run the algorithms, the routing, distributed routing algorithms. But we don't have a single point of failure, so it allows for dynamic reconfiguration. So if something in the network fails, we should still be able to operate other parts of the network and route around problems. And that's the advantage of distributed routing. So let's continue and let's talk a little bit about the fundamental mechanism employing distributed routing. And if you think about a small network that you might have a few routers, something like that, the fundamental mechanism is going to be the exchange of messages, exchange of what we're going to call updates or routing updates. And what is a routing update? It's a messages overhead that tells the other router what nodes you can see. So this, let's say R1 can actually see these three routers, and it will also send the update when it cannot see them. So when the link goes down, for instance, it will tell the other routers that it cannot see a particular node. Now this is not done in, that's a generic concept. And there's two protocols or two algorithms that we discussed in other videos. One was distance vector and the other one was link state. And when you think about distance vector, the principle behind distance vector is that any node, so a node, will send updates, these routing updates, to its neighbors. And before we continue with this part, let's write down what happens with the link state routing. In this case, a node will send routing updates to the entire network. So that's a huge difference between these two. One, it's only going to be sending updates to its neighbors. Now it's to the entire network. And the difference is that in distance vector, remember this is distance vector, in distance vector, a node will send updates to its neighbors, and those updates are going to be, they're going to be about the cost to reach all nodes in the network, or at least all nodes that it knows of at that time in the network. So in a very large network, you're going to send a very large message containing all the updates because you need to tell your neighbors about all the nodes in the network. On the other hand, on link state, you will send routing updates to the entire network, and those updates are going to be just about the cost to reach your neighbors. So that's a fundamental difference in the principles of how these two algorithms operate. So let's look at an example of a distance vector. In a separate video, we look at a detailed example of a link state and digital algorithm. Now let's look at a separate example, or specific example for distance vector. We're going to do this step by step. Here we have a network, the network with three nodes, nodes A, Y, and Z, routing nodes, so X, Y, and Z. And we have the costs between every pair of nodes as 2, 1, and 7. And we're going to do this step by step using the tables that are right here. And what's going to happen is that as we progress in time, we're going to move from left to right. So we're going to start here and we're going to be moving in this direction. Right here we have a table that is going to allow us to write down right here. We have a table that allows us to write down the distance to the other nodes that we know of. Okay, so basically the distance vectors. The first one here, this row here, is going to be for node X. So everything over on this first row is going to be, all of this is going to be for node X. The next one is going to be for node y. So the next one over here, this is going to be for node y, this row. I'm not going to mark it, and the last one is going to be for node z. Okay, so remember, time progresses as we move from left to right. And the initial routing tables is the first one right here. So we start first in time, we're in this column right here. And we start here, the first thing that we're gonna write down is what we know about, in this case, every other node in the network. So if you're node X, what do you know? You know that, let's look at our topology here. If you're node X, you know that obviously going from X to X has a cost of 0. Going to Y, you know that it has a cost of 2. And going to Z, you know that has a cost of 7. And if you're node X, you have no idea how the values or the distances from Y to any other node or from Z to any other node. Why? Because you just started. You have not received any updates yet. Let's go to the second one here. If you're Y, you know that you can reach node X at the cost of 2, node Y at a cost of 0, because from Y to Y, and node Z as a cost of 1. And the same way, we're going to write infNet here because node Y doesn't know anything about how X or Z reach any other of the nodes. If you're node Z, you know that you can reach Z at a cost of 7, Y at a cost of 1, and Z at a cost of 0, because it's going from Z to C, and again, nothing else. So what's going to happen next? What's going to happen next is that, let's look at node X. Node X, right here, is going to receive updates. It's going to receive a distance vector update from node Y, and a distance vector update from node Z. What is the distance vector update? These are the distance vectors. So for instance, this one right here, let me mark in a different color. This one right here is the distance vector. I'm going to mark it like this, D vector for X. This one right here is the capital D vector for Y. And the last one here is the capital D vector for Z. So they're going to exchange these vectors. So X is going to tell Y and Z about its values. So let's draw lines to illustrate that. And what we're going to do is, let me zoom out a little bit. Here we're going to go zoom to 100%, I believe. Yes, that works. And what we're going to do is we're going to say that X is going to send this message, this vector, to Z. It's going to be sent this way to Z, and it's going to appear here. So let's do that. And Z receives this message from X. And what's going to happen is that it's going to, in this second step, it's going to say, it's going to receive the message that says 0, 2, and 7. That's what X tells Z. Now X also tells, X tells Y. Now X also tells Z and sends this vector right here. So let's put it all the way down. Let me scroll down. It's going to send all of this to Z. It's going to put it right here. It's going to be the same message. It's going to be 0, 2, 7. So this is the vector that X sends to Z. Now Y is also going to send it to X and to Z. So this Y is going to go, and from Y is going to go here. Oh, let me use a different color. I'm going to use maybe green here. So Y is going to send this here. Oops. I want that to be green. Okay, there you go. So Y sends this here to X, and Y is also going to send it here to Z. And what are the values that it's going to be sending? It's going to send the values 2, 0, 1. So let's write those down. It's going to send 2, 0, 1. I'm also going to send 2, 0, 1 to Z. And now we have to mark what happens with node Z. And node Z, let's mark in a different color. We're going to use yellow. It's going to send this vector to X. So let's move it up here. It's going to send this vector to X. And it's going to say the vector says 710. And it also sends that vector to Y. Excuse me, let me change the color. It also sends that vector to Y. And it says from Z to Y, it says 710. Oh, excuse me, I marked it in the wrong place here. Erase it there. It says from Z, it goes all the way to Y. And it says 710. 710. Okay. No, excuse me, I just noticed that I marked this one wrong place. When we receive this one from Y, we actually receive it over here. So when Y sends its update, it's going to be sent to Z, and it's going to be sent right here. So 201 we have to write right there. So let me erase it from here, and we're going to put it over here as 2. Change colors. I want to change the color for me. There you go. Okay, and it's going to say 201. So 201. Okay, so we have received all the vectors from the other two nodes here. So let's look at our network here with X. So X knew that it could reach Y at a cost of 2 and then Z at a cost of 7. But now it has received a message that says that Z can reach Y at a cost of 1 and can reach X as a cost of 7. And also says a message that Y can reach X as a cost of 2 and Z as a cost of 1. So this one's interesting because now X knows that if it goes through Y, it can reach Z at a cost of 2, plus 1. So X recomputes this and say, well, from X to X there's always 0. From X to Y, nothing has changed. The minimum cost is 2. However, from X to Z, I can now go through Y, and I can do this at a cost of 2 plus 1, or 3. Okay, let's see what happens with Y. So Y receives this message, and it checks and says, if I am Y, can I reach X or Z at a lower cost with these updates that I have received? And the answer is no, because X, as you see from the figure, we can still do this at the cost of 201. There's no way to do it at a lower cost. If we go and look at Z, so Z at first was reaching X directly at a cost of 7, but now it can go through Y at a cost of 3, and can go to Y directly can reach X at a cost of 3, can go to Y at a cost of 1, and obviously from Z to Z is 0. And after that, they're gonna exchange this one more time. So I'm not gonna use the same colors again, or the same arrows again, excuse me. But we're gonna say that X is gonna send this to Y. So X is going to tell Y that it can reach this as 0 to 3, and it is also going to send this new 0 to 3 value to Z. Why does it do this? Because notice this. There was an update here. This value went from 7 to 3, so this means that X is going to send this update to everybody else so that the rest of the nodes know about this. So X sends that to Y and to Z, and Y also has a change. Y, notice that it has a change. Excuse me, Z has a change. Z went from 710 to 310. So Z is going to tell, and it's going to tell everybody that it can reach X at a cost of 310. Oh, sorry, 3, and then Y at a cost of 1, and here Z at a cost of 0. So again, here's what we get. We get 3, 1, and a 0. On top of that, X has not received anything additional from Y, so it's still going to use 201. Hasn't changed, but it's going to use that last value. So the same thing as here. Y is not going to send an update, so this still stays at 201. And Z does not receive an update from Y, so this is still at 201. And Z, let's go with X. So X gets this new information and see if it can reach any of the nodes at a lower cost, and that is not the case, so X continues to use the cost of 023, and the same way with Z. Z is a cost of 310, receives these updates, and there's no change in the least cost paths from Z to the other nodes, so it continues to do this at 310. So that's the way that the distance vector algorithm works, based on the exchange of these messages and exchanging messages when there's updates to the network, as well as periodic updates that are sent through the network, so that other nodes know that the links are still active. Those updates are now known as heartbeats or keep alives. Now let's see what happens and some problems that we're going to have with distance vector. And the first thing that we're going to look at is what happens when there's changes in the network. And in this case, the changes is going to be a link cost change. Sometimes the link is going to go down, sometimes it's going to go up. Let's look at the first case when the cost decreases. Okay, so in this case, we're assuming that the cost of the link from X to Y has decreased from 4, to 1. This might be because, for instance, there's less traffic on the network, and maybe the cost was proportional to the available throughput, so the cost went down. So if we look at what's going to happen here, let's go step by step. So we only need to analyze what's happening between Y and Z, as you'll see in a minute. So what interests us is Y and Z, and its cost to X. So let's look at what's going on. So the first thing that we're going to notice is that node Z, detects the change. So detects the cost change. Okay, what change? The cost of, before it had a cost of 4, and then now it has a cost of 1 to going to X. So what it's going to do is going to update its distance vector, and it's going to tell the neighbors about this new change from 4 to 1. Excuse me, here is not Z. Y is the first one that detects this because Y is right there. So again, Y detects this first. Now Z is going to receive the update. So Z receives the update. The update from Y, where it informs it of the new change, and the same, an update is stable. It receives it there, and as that is stable, and now the cost to reach Z to reach X from Z, which it used to be 5, now the cost is going to go from 5 to 2. So nothing special there. And of course then Z updates its cost, so updates its distance vector, and it tells the neighbors. So nothing special there. So Y is going to receive now the update from Z to the next one. So the Y receives the update from Z. And Y receives it away from Z. And again, update its tables and notices its costs are not going to change because Z is not providing any new path at a lower cost, are not going to change. So does not send any updates. Doesn't send any updates. So if that's the case, then the network has reached a stable state very fast. Okay, so basically we needed just two interactions, and we were done, and then we stop. That's it. We are done, and we're gonna say that in the case where the cost goes down, so it's good news, right? The cost of the network has gone down from 4 to 1 of that link, and we're gonna label this condition as good news. In the condition, we're gonna say that good news, and we're gonna say have traveled really fast. Good news travels fast. Okay. Okay. So what happens in the other case? Let's look at the case where the cost is going to increase. So now the cost of going from x to y is going to go from 4 to 60. So let's again see what happens with y. I'm interested in what's going on with y. So before this change of going from 4 to 60, y thinks that it can reach from y to x. It knows that it can reach it at a cost of 4. From y to z, it knows that it can reach it at a cost of 1. And also y knows that z can reach x at a cost of 5, because that's the vector that z had sent. It says I can reach x as a cost of 5. So then we're going to assume here that at this point in time, then the cost goes from 4 to 60. So when a 4 goes from 4 to 60, then y recomputes its value. So then y recomputes its vector, and it says now going from y to x is going to cost me 60. Going from y to z is going to cost me 1. But C just told me that it can reach x at a cost of 5. So it says with this information, y believes that it can reach x at a cost of 6, because y thinks that since C told y that it can reach x at a cost of 5, now y thinks that it can reach x through z at a cost of 6. And of course, y knows that it can reach z at a cost of 1. So obviously here, we have a problem, because this is not true. This is false information. And it's based on the fact that before the change, z has told us that it can reach x at a cost of 5, which was correct before, but that is not correct anymore. So what's going to happen next is that then y informs z of the new change. So y informs z and tells z I can reach x now at a cost of 6. So y tells z, going from y to x now costs 6. So z recomputes. So C recomputes this distance vector and says y can reach x now at a cost of z, since the cost going from z to y is 1, then C thinks that Z thinks that it can go from Z to X now at a cost of 7. And this is again incorrect. And it was based on the fact that Z knows that it can go to Y at a cost of 1. So Z informs X. So basically Z, excuse me, we need Z informs Y. We're only looking at Z and Y. Z informs Y. And so Z tells Y, I can go, the cost of going from Z to X, it's now 7. From Z to X is now 7. And obviously the cost from going from Z to Y is 1. And now what's going to happen is that Y thinks that it can reach X at a cost of 7 plus 1 or 8, because Z just informed that it can reach 7. At 7, then Y thinks that since Z is a 1 hop away, then the cost of going from Y to Z is not 7 anymore, but it's 8. And this will continue, and the costs, notice that the costs that Y and Z believe they can reach X keeps going and going up until this cost right here from Z actually sees that it's more expensive to go through Y than to go directly to C at a cost of 50. So this is going to keep growing. So all of these are mistakes. They're going to keep happening, keep happening, and keep happening. And the problem is that this creates a routing loop. The problem comes from the fact that Z is telling Y basically a lie based on what it had known before, and Y is taking this lie and computing a new value and telling it to Z, and Z uses to compute this new value, and so on. So we have a routing loop here between Z and Y, and the packets go back and forth until the cost between these two grows and is higher than 50. And you can check that, and you see that it takes a total of 44 steps to do this. And this stems from the fact that Z is telling Y, C is not telling Y that is actually using Y to reach X. And that's the main problem that we have here. Now, in contrast to what we saw before, bad news travels very slow. Okay, so this change from 4 to 60 propagates very slowly in the network. In this case, 44 steps. So imagine what happens if for some reason the cost here was very high, was in the order of the thousands. So it will take several hundred steps, over 950 steps maybe, in order to reach this condition. And in the meantime, the packets just loop around and loop around between Y and Z. And that all of this stems from the fact again that Z is not telling Y that it's using Y to reach X. How do you fix this condition? Well, a solution. And the solution is called Poisson reversed. And what it means is that in this case, C is going basically to lie to Y, and it is going to tell Y that its cost to reach X is infinite. So what this means is that, well, why? Because Z uses Y to reach X. So any node, in this case Z, is going to tell Y, is going to tell a lie and say, cannot reach X. So Z tells Y, I cannot reach X. Why? Because Z knows that it's going to use Y to go to X. So anytime that a node is going to use another node to get to a destination, it's going to introduce this on purpose lie. Why? Because in that way, what's going to happen is that the other node is not going to use the first node to reach the destination. In this case, if Y knows that Z cannot reach X, Y is never going to reach, is never going to use Z to go to X, and we're going to avoid this problem. In this case, once the cost goes up, then since Y is never being told by Z that it is using X, we will not go into this routing loop and count and keep counting up in a very slow way. What's going to happen then in that case is that eventually Z or X is going to tell Y that it can reach Z at a cost of 50, and now if Y wants to reach X, it's going to go directly to X, and if it wanted to reach Z, it's going to go directly to Z at a cost of 1. Now, this bad news travel slowly is also known as the count to infinity problem. Why? Because again, if the cost of the links are really high, you're basically counting up as we saw here. We started at 6, then we went to 7, then we went to 8, and we're gonna go to 9, eventually until we reach a cost higher than 50, and that's gonna take 44 steps. And that's also known as the count to infinity problem, and it is solved with this solution called Poisson reverse, where any node that is going to use another node to reach a destination is going to lie about the cost to reach this first node. So let's go back to our lesson plan. The last thing that we're going to look at is how to install GNS3 on our VM or droplet from DigitalOcean. To do this, you're going to watch a separate video that starts from scratch, creating a VM, and finishes once GNS3, which is a network emulator, is configured with some free HP switching routers, virtual switching routers that we're going to use to test routing and test addressing in the coming weeks.